All right, we left off talking on Friday about passive transport. Okay, so passive transport is moving things into and out of the cell without using ATP, right? So we don't have any ATP being used. Okay, and we always move from a what concentration to a what concentration? High concentration to a low concentration when we're looking at what is moving, okay? And we are starting right here with osmosis specifically. Okay, so osmosis specifically is going to be the movement of water. Okay, so the unassisted diffusion of a solvent, usually water, through a membrane. Okay, now, I'm a little disoriented because my computer's not working, but it's okay. All right, so when we talk about osmosis in water, water is going to move from a high concentration of water to a low concentration of water. Okay, it's still following our passive transport rules. However, it is very, very difficult to measure concentration of water itself, of the solvent. So instead, we are going to look at the solute, or what is dissolved in the water. Okay, so how salty it is, or how sugary it is. Okay, so how much the solute is dissolved in there. Okay, so we are going to change our definition a little bit. Okay, so osmosis, the water is still moving from high concentration of water to low concentration of water, but we can also say that it moves, the water moves from less solute concentration to a high solute concentration. Okay, so it's moving from low solute to high solute, okay, or from low salt to high salt, because the amount of salt that's present is going to be opposite from the amount of water that's present when we're looking at a solution, okay? So, another way to say this, so that's the fancy science way, and you'll probably see that definition written on a test. You'll want to choose that one, okay? Low solute to high solute. Another way to say this, more practically, to help you solve these problems, is that salt pulls water. Salt pulls water. So wherever there's more salt, that's where the water is going to go. Okay? Because the whole purpose is to reach equilibrium, where it's the same amount of water, or the same amount of concentration on both sides. Okay? So for example, let's look at one of these YouTube experiments. Okay? YouTube, there is a tube that is U-shaped. Okay? And we're going to put in the middle of the U-tube a selectively permeable membrane. That membrane will allow water to move through, but it won't allow the solute, or the salt, to move through. Okay. On our picture, we've got 1, 2, 3, 4, 5 solute particles over there on that side, side A. And we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 solute particles on side B. Okay? So there are more solute particles over here on side B. We want to even things out. We want there to be the same ratio of water to solute particles on both sides. In order to do that, which way is the water going to move? To the right or to the left? To the right, over to side B. Okay? And we know this because salt pulls water. There's more salt, there's more solute over here on side B. So the water is going to flow across that selectively permeable membrane into side B. Okay? And when you do this experiment, I don't know if you guys did this in high school, if you use one of these YouTube things, but you end up having a higher volume of water on side B than you do on side A. And it looks really funny because it looks like it defies the laws of gravity, but it's not. Okay? Questions about this basic principle. water goes towards the higher salt concentration. Yeah. The goal is for the concentration, the ratio, yeah, of water to solute particles to be even. Yeah. Okay, any other questions? Okay. All right, now we're going to look at some examples of this. As long as you know that definition, what you need to know, more importantly, is what happens in specific situations. Okay? So we are looking at red blood cells, okay, that are found in your blood vessels. Now, you who are entering the medical profession, which I know is not all of you, but some of you guys are entering the medical profession, when would you be introducing new liquids into the blood supply? When you're starting an IV, right? So when we're putting liquid around these red blood cells, we need to know what that liquid is going to do to the red blood cells, right? Okay. So there's three different options. We can insert a solution that is isotonic, we can insert a solution that is hypertonic, or we can insert a solution that is hypotonic. Okay? So we're talking about the solution that we're adding around the blood cells. Okay, I'm going to make us a chart because that's the way I organize information more easily in my notes. If it helps you, do it. If it doesn't, you got the words over there. Okay, so our solution could either be isotonic, hypertonic, or hypo. Okay. The first thing we need to figure out is, what does that mean? Okay. So, these terms describe the solute concentration of that solution you're adding around the cells. Okay? So our next question is solute concentration. Okay? We'll use salt as our example because salty water is something we can think about pretty easily. Okay? So if we add an isotonic solution to our cells, that means that the amount of salt, the concentration of salt, is the same outside the cells as it is inside the cells. Okay? So the solute concentration in the isotonic solution is equal. Okay? The next solution is a hypertonic solution. Okay, from your knowledge of cells and background information and your reading you've already done, what do you know about hypertonic solutions? Is there more solute or less solute? Oh, I'm hearing both. Okay, a hypertonic solution has more solute, hyper or above. So hyperactive, you are super active, right? So a hypertonic solution has a super amount of solute. Okay, so we have lots of solute there. So an example of this would be salt water. Okay, it's really, really salty. Okay, so iso is equal. Hyper is more solute. That means hypo is going to be less solute. Okay, so that means our solution around our cells has less salt than the cells themselves do. So what's an example of something that would have less salt than a cell? Just plain water. Yep. Okay, so just plain water has how much salt? No salt, right? So that is a hypotonic solution. It has much less salt than you would find inside of a cell, right? Okay. So hypo is below, is less. Hyper is more. Iso is the same. Okay. So that's our second thing we need to know is which way the water is going to move. Okay, so water will move. Okay, remember our rule, salt pulls water. The water is going to go towards where there is more salt. Okay? So in an isotonic, there's equal inside and outside. Which one's going to pull the water more? Neither, because we're the same. Right? So overall, our water will move. It's going to move in and out at the same rate. So overall, we have no net movement of water. I'm going to add another one down here so that I have to draw. I'm going to draw a picture. That's about the same concentration inside and out. Okay. The next one is hypertonic. We said that there's more solute where? In the solution outside the cell, right? So we may only have like 2 dots inside. But in the solution, we're going to have a lot. Because it's a hypertonic solution. We have a lot of solute, a lot of salt. Okay? Salt pulls water. So which direction is the water going to move? Out of the cell. Okay? Good so far? Okay. And our third option says that there is less solute in the liquid around the cell. So inside, we're going to have some dots. But we're going to say he's using water. So there's no dots on the outside. Okay, so there's less outside, more on the inside. Salt pulls water. So which direction is the water going to move? Into the cell. All right. So now we've got the isotonic. There's no net movement. Hypertonic, the water is going to move out of the cell. Hypotonic, the water is going to move into the cell. Now, the final piece of information we need is what's actually happening to the cell. Okay? And we can infer those based off of which direction the water will move. Okay? So we're going to say cell will. And we're going to talk about the shape and the size of the cell. So in the isotonic solution, the water is moving in and out at the same rate. What's going to happen to the size and shape of the cell? It's going to stay the same, right? So the cell will not change. Okay. So isotonic, same, no movement, cell's not going to change. Okay. Hypertonic. We had more solute in the solution. The water is moving out of the cell, so the cell will shrink. Okay. Another way to say this is to say crenate. Okay, so crenation is shrinkage. And the last one is hypotonic. Hypotonic, there's less solution outside, or less solute outside, sorry. Water is going to move into the cell, and if water moves into your cell, what's going to happen to him? He's going to swell. And if too much goes into the cell, he can burst. Is it good for your red blood cells to burst? No, it is a bad thing. Okay. So, I told you how I remember hyper versus hypo, more solute because it's hyperactive, there's a lot of solutes there. Okay, the way I remember whether it's going to shrink or swell is because a hypotonic solution causes your cell to turn into a hippo. He's ended up looking like a pig. But you get the point. There he is. Okay. So, hypo, hippo. If you put a cell in a hypotonic solution, he's going to swell up like a hippo. Okay. Now, when you are starting an IV and giving it to a patient, what type of solution do you want to inject into their veins? An isotonic solution. Okay? Always inject the patient with an isotonic solution. If you inject them with a hypertonic solution, what's going to happen? The cells are going to shrink. Do cells do their job if they're not the right shape? No. If you insert a hypotonic solution, what's going to happen to their cells? They're going to burst. The cells function well if they're bursted. No. Eventually, you'll die. Okay, so we've got our solutions. We know we're going to inject the patient with an isotonic solution. So when you start an IV drip, one of the first bags you put on is a saline solution, a saline chloride solution. That saline solution is an isotonic solution. And then you put your drug into that isotonic solution to get into the patient. Okay, and that's why. All right then. Okay. Questions about hyper, hypo, iso, and what's it going to do to a cell? All right. Did anybody do the lab in high school where you took eggs and you took the cells off and put them in different solutions? Who was that ever? Okay. If you haven't, look up a YouTube video of deshelled eggs. They're fantastic. All right. So now that you know what you know about osmosis, chat with a partner, somebody around you, and see if you can figure out an answer to this question. At that time, I will also pass out the cheat sheet. So, chat for a second, see what you think. I'll give you this direction, this hint, this leading bit of thought. We are making your gut a certain type of solution. We are making it either hypertonic, hypotonic, or isotonic. Okay. So, when you get sick with this bacterial infection, you're irritating the intestinal tract, it interferes with digestion, and what happens, isn't this a beautiful intestine I have right here? What happens to this area inside your intestine? It becomes what? Yes, it becomes hypertonic. Okay. Okay, so inside your gut becomes hypertonic. If it is hypertonic, what's it going to do to water? It's going to pull the water towards it. Okay, so hyper means there's more solute there. Okay, so there's lots of solute here, lots of little dots. And it's going to pull the water. So the water is going to come in from the blood supply that surrounds the intestines. It's going to fill up this area with a lot of water, which is going to make gonna make you have diarrhea. Okay, it's gonna give you liquidy poopy. Okay, because the water is being pulled into the intestines. Okay, and what's actually happening is the bacterium causes increased chloride ion secretion. So you're increasing the salt that's being put into the intestines, and so your body wants to put water there to dilute the salt, and you end up with a big mess. Okay. So that now is the end of passive transport. Good? Questions, thoughts, ideas? Okay. So now we are looking at the other form of transport, which is active transport. If we are doing active transport, we have to use ATP. Okay. You guys ready for a question to see if you remember what we talked about on Friday? Okay. Adenosine triphosphate is ATP. How many phosphate groups are there? 3. Where is the energy stored? Between that second and third phosphate. Okay, so the energy is in ATP. If we want to get rid of energy, we break off a phosphate and we end up with what two things? ADP and phosphate. If we want to store energy, what do? Put ADP and phosphate back together and you end up with ATP. Okay, good. So in these processes, we are taking ATP and we are breaking off a phosphate group. We're changing it into ADP so we can get the energy to do these things. Okay? So types of active transport. First, we call this first process just active transport, which I know makes a lot of sense, right? A type of active transport is active transport. Okay? But it's also called solute pumping. There isn't a separate slide for this process, so let's talk about it real quick. There is a slide of an example that we'll get to in a little bit. Okay? But solute pumping requires ATP. You have to have a protein to get it across the membrane. So we use protein pumps. Okay? And these protein pumps are always pumping from a low concentration to a high concentration of whatever they're moving. Okay? So they're going to move things from where there aren't many of them to where there's already plenty of them there. Okay, we're just amplifying our effect. Okay, so that's active transport or protein pumping or solute pumping. Okay, the second type of active transport is vesicular transport. And we're going to have some slides to cover this information. Okay, but a vesicle, you'll see the picture on the next slide, is a little package that's surrounded by plasma membrane. Okay? And these little packages can come into the cell, and they can go out of the cell, and they're named based on what they carry and which direction they're moving. Okay? Are y'all ready? Okay. Let's look at each of these. So our first one over here is called phagocytosis. Phagocytosis is where a cell engulfs a large particle. So we're eating something really big. The phagocytosis is eating something really big. And you can see the cell membrane kind of forms of arms, these little pseudopods, around whatever they're eating, and then they'll break it off and bring it into the cell in that little package, in that little vesicle. Cells that do these are called phagocytes. So an example of a phagocyte is a macrophage, part of your immune system. They go around and eat bad things, so they go around with bacteria or cells that have died, and they get it into the cell and then break it down into little pieces. Other things that aren't in your body, like amoebas do this so they can eat. All little ones that organisms. Okay, so phagocytosis is cell eating. You're getting things in. Okay, our next type is exocytosis. Which direction are we sending that vesicle this time? Out. So exocytosis, we're sending it out of the cell. again, you've got some type of little vesicle, little package. It fuses with the plasma membrane and releases what was inside the package outside the cell. Okay, so exocytosis is exiting the cell. But again, both of these are pretty complex processes, and they require ATP to happen. Okay? Questions about those two? And then our last two, penocytosis, you'll also see it as bulk phase endocytosis. Okay, both of those are the same process. Okay. This is endocytosis, so which direction is the vesicle moving? Into the cell. Okay, but this time, instead of engulfing something really big, I had this fixed on my PowerPoint on my computer. Okay, but we are engulfing mostly liquid and whatever is dissolved in it. Okay? So this isn't going to be something really big like those phagocytes engulf. It's just a cell gulping up some of the fluid around it. Okay. And then whatever's in there will also come into the cell. It's very non-specific. Just grabbing stuff. Which leads us to our last one. Our last one is receptor-mediated endocytosis. Okay, so again, it's endocytosis, so we're bringing things in. And it's receptor-mediated. What do you think that means? What are we going to use? Receptors. Okay, so receptors are going to be here in the vesicle, which allows you to only pick up what you want to pick up. So we're bringing specific things into the cell. Okay? Bring specific things into the cell. An example of this in your body is LDL, or low density lipoprotein, LDL cholesterol. He only enters the cell when he binds to his LDL receptor. So the LDL receptor is all on the surface of the cell. Once LDL binds to it, it sucks it up. And now you have a little vesicle with LDL inside of it, inside the cell. If you're picking up a specific thing because you have a receptor there that's going to bind to something specific outside of it. Okay? And again, all these, because they're pretty complicated processes, they involve your vesicles, they require ATP. So they are active transport. Okay? Feel good? All right. Now, we talked about the function or the structure of the plasma membrane, what makes it up, the phospholipids and the proteins and the carbohydrates. And we talked about moving things across the membrane, but that's not all the plasma membrane does. So there's some other things that are very important for our plasma membrane to do. Okay, and one of those is generating and maintaining a resting membrane potential. Okay, so I'm going to draw us a picture over here. Remember, guys, I told you at the very beginning that we're going to do lots of beautiful pictures. I do not lie. There's lots of beautiful pictures. Okay, so a resting membrane potential means that if you were to measure the voltage across this plasma membrane, let's say you take a little electrode and you measure from out here to inside the cell, your little voltage meter is going to register a difference. There is a flow of ions across that membrane. Okay? And for a usual cell, it's usually around negative 70 millivolts. Okay? So voltage is the electrical potential energy resulting from the separation of opposite charges. So what that means is, across this membrane, there's going to be one side that is negative is positive. Okay? So what we end up with is the negative is on the inside, and the positive is on the outside of the cell. So there is a slight difference of charges between the inside of the cell and the outside of the cell. Okay? From what you know already about chemistry and cells and how they function and do their things, how are we going to get a difference in charges? How are we going to get something positively charged on the outside, and something negatively charged on the inside? What do you know of its charge? Hear people whispering. Ions. That's exactly right. So remember, ions can be positively or negatively charged. So we're going to have a separation of those ions. We're going to have things that are more positively charged right here on the outside of the cell. And we're going to have things that are more negatively charged on the inside of the cell. So it's going to give us a separation. There's going to be a positive side and a negative side of that positive ring. Okay? So I think that covers all we got here. The resting membrane potential anywhere from negative 20 to negative 200 millivolts. But usually it's around negative 70. And at rest, the inside is negative compared to the outside. Now, the last thing here is how do we get that separation of charges? We talked about the ions, but how specifically does that happen? Okay. There's a couple things that are going on here. The first thing is a concentration gradient. So we have a separation of those ions. Sodium is at a higher concentration outside the cell. So sodium is high. Outside, which means that sodium is low inside. And this is an ion, so it's got a positive charge. Okay? Potassium is the opposite. So potassium, K, is low outside, and potassium is high inside. Okay, so that's our first difference between the inside and outside. We know we have a positive charge outside, negatively charged inside, and we've got this difference in sodium and potassium. But so far that hasn't explained anything because sodium and potassium are both positively charged, right? So we've got positive inside and we've got positive outside. How do we have this difference? Okay, so that comes to the next thing we got here. Okay? There's a differential membrane permeability. So at rest, when the cell is just collapsing, the membrane is more permeable to potassium than sodium. Okay? In the membrane are these leaky potassium channels. There are those big purple things there. I'm going to draw them on our picture right here. Okay? So there's my little potassium channel. Okay. What do you know about diffusion and the way things normally want to move? They want to move from high concentration to low concentration. So which direction at rest are my potassium ions going to want to move? Inside the cell or outside the cell? They're going to want to move outside the cell. Just because they leak. Okay? And they're going from high concentration to low concentration. Okay, so as that happens, the potassium amount is going to go down and down and down and down and down. Okay? So that's going to reduce how much positive is on the inside of that cell. Okay, so it's getting us closer to some negative number. Right? Another thing that happens that isn't part of the bullets, but it's in this picture here, is that inside the cell, there are proteins that have negative charges. These are the proteins. And they're large. They can't leave. Okay. So that also adds to the amount of negative that's inside the cell compared to the outside of the cell. Okay. Now, finally, it says because things would just move down their concentration gradient and we end up balanced. So our membrane is going to use our sodium-potassium pump as a form of active transport to maintain our potential, to keep the amount of sodium higher inside than outside, and to keep the amount of sodium higher outside than inside. Okay, before I click the next slide, are there any questions? I know this is kind of a different concept. Yeah. So no, we're trying to keep it from being equal. We're trying to make the inside more negative and the outside more positive. Okay, and the reason why we're doing this is so when our cell wants to send information, like a nerve impulse or muscle contraction, we're going to be able to change this membrane potential pretty quickly. And that change in potential is going to be called an action potential. And that's going to be what actually carries the information, because we're changing the charge. But first we have to set a charge up so that we can change it. Okay, that's what all this is leading up to. Okay? Questions? Any more about what we got? Okay. So the next layer of this is our sodium-potassium pump. Oops. There we go. Okay? And the purpose of the sodium-potassium pump. The purpose of this sodium-potassium pump is to get the sodium outside and potassium inside. Right? Because that's what we want. We want high sodium outside. We want high potassium inside. That's what we want to set up. Okay? This sodium-potassium pump is going to do that. He's called a sodium-potassium ATPase pump because he has to use ATP to do it. Okay, so here's what's happening. You've got this protein, and I've got a video of this that I'll look up in a second in my other PowerPoint, but it'll be okay. We've got this protein, this pump. It binds to 3 sodiums that are coming from inside the cell. So it picks up 3 sodiums from inside. Then it uses ATP, it flips it around, and it releases those 3 sodiums. Great. It releases those 3 sodiums outside the cell. Okay? So we're going to draw another picture of our sodium-potassium pump. And he is sending 3 sodiums out. But then while he's flipped outside, he's going to pick up 2 potassium and open back up on the inside and release his 2 potassium inside the cell. So you end up doing this flip-flop and removing 3 sodiums from the cell and only putting back 2 potassium. Yeah. Okay. Both sodium and potassium have positive charge, right? But we're trying to get the inside to be more negative. So if we take away 3 positives, but only put back 2 positives, we have a net negative on the inside. Okay? So it's all about keeping the inside more negative than the outside. Okay, so we take out 3 positives of the sodiums and only put back 2 positives of the potassium. And this keeps running and running and running. And we keep moving the sodium out and the potassium in. This process requires a whole lot of ATP. So about 70% of the ATP that's produced for the mitochondria in certain cells will go to this pump that is moving sodium and potassium inside and out of the cell. That's a whole lot of ATP used for just this. Okay? You either have to find that cricket and kill it. He's so frustrating. I don't know where he is, but he needs to die. Okay. Okay. So that's our resting membrane potential. We're making it more positive outside, more negative inside, and it's because the separation of sodium and potassium, we've got negative proteins inside, and we are switching the sodium and potassium at a 3-to-2. Okay, we're not 3 to 3. We're not equally putting out positives and taking in positives. We're putting out 3 positives and only taking back 2 positives. Okay, so that sets up this difference across the membrane. Okay, questions? Because my next slide is not about resting membrane. After this, it's over. Okay, so this process, you do it for this test, but it is going to come back, and it's going to come back a lot. Okay, so if you need to talk with me about this process and make sure you got it, let me know. Okay? I tell you what, instead of finding the videos, which is not directly in my PowerPoint, I will send you guys a link to the YouTube video of the sodium potassium pump. If you want to see how it switches the 3 sodiums for the potassiums, watch it. If not, it's okay. It's not the end of the world. Okay. Other functions of the plasma membrane, we're going to hit this pretty quickly. So the plasma membrane is involved in cell-environment interactions. So it helps the cell interact with what's around it, which makes sense because he is the outside of the cell. Okay? So the interactions are going to involve the glycocalyx molecules, and the glycocalyx molecules include both glycolipids, which we've talked about before, which are the lipids with the sugar attached to it, as well as glycoproteins. What do you think glycoproteins are? Sugar proteins. Okay, so proteins with the green sugars stuck to them. Okay? They're responsible for adhesion, so helping the cells stick to the outside environment. And they also function as membrane receptor molecules. So this is really important in immunity. These will help determine both inside your body what type of cell you are. So let's say you're a liver cell. You'll have carbohydrates on your surface that say, I'm a liver cell. But it's also you-specific. So the carbohydrates on my surface say, I am a Dr. TG liver cell. The carbohydrates on your surface are going to say that you are not a Dr. TG liver cell. So if I take one of your livers and put it in place of my liver, I don't have one yet, then my body is going to see those carbohydrates and say, uh-oh, you don't belong here. And then my immune system is going to attack it and try to get rid of it. All because of these carbohydrates in the surface. All right, that's where you get rejection and problem. All right, this next section we're going to hit pretty quickly because this was your homework. Okay, we're going to go through some of your organelles. We've got a couple more minutes here. So, first of all, the cytoplasm. We talked already about the difference between the cytoplasm and the cytosol. So the cytoplasm is the material between the plasma membrane and nucleus. The cytosol is the liquid. That cricket, oh my goodness. It is so frustrating. Okay, between classes, somebody kill it. Okay, the cytoplasmic organelles are the little organs that live inside the cell. He knows we're talking about them. And then finally, inclusions. So inclusions are included, but they are not themselves organelles. So for example, glycosomes are glycogen granules. So just big clumps of glycogen, big clumps of sugar. And so cells that need a lot of sugar have these glycogen granules in them. So muscle cells, they need sugar so they can make lots of ATP so they can do their job. Okay? Lipid droplets in fat cells. So fat cells have these big pockets of lipids. They're not organelles, but they're inside the cell, so they're called inclusions. And pigment, so melanin granules that you see in your skin that gives you the color of your skin, the color of your hair. They are also found in the cytoplasm as inclusions. Okay, they're not their own organelle. And crystals. So for example, uric acid crystals are an inclusion. So if you know anybody who has gout, maybe somebody who has a big toe that really hurts that joint, because they have a bunch of uric acid crystals in the joint. It hurts bad. All right. Next. Mitochondria. Okay, so what did you guys put as your short definition for a mitochondria? Powerhouse. Okay, and more specifically, powerhouse is good, but he produces what? ATP. Okay, that's your big thing about mitochondria. He produces ATP. Okay. So there is not the same number of organelles in every cell. So some cells have more of certain organelles because that's what they need. So if you're a muscle cell, you're going to have lots of mitochondria because you need to make lots of ATP. You need to convert a lot of energy, right? So that you can do what you do. Okay, a liver. Liver does a lot of things. We'll talk about him more next semester. But he also has a lot of mitochondria to get lots of energy. Okay? So in saying that he produces ATP is saying this bullet right here. He carries out multi-step aerobic respiration, so he uses oxygen in the process to make ATP. He also breaks down metabolites, oxidizes them, and converts them to ATP. That bullet just means that he can also use fats and other things to make ATP. Okay? So all this just means he makes lots of ATP. Okay? This is a picture of the mitochondria. You aren't going to be asked to label one, but the structure will come in handy when we talk about metabolism next semester. Okay, he's special because he has two membranes. He has his outside membrane, and he has his inner membrane that has lots and lots of folds. Why does a mitochondria have lots of folds on the inner membrane? It increases surface area. Okay, so there's lots and lots of room for all these processes to happen. Okay? Oops. All right, y'all didn't see that. Okay, that was your quiz for Wednesday. Okay. Endoplasmic reticulum. Endoplasmic reticulum. Okay, I got 2 more minutes. Let's see if we can get through the ER. Okay? So the endoplasmic reticulum, you've got a rough ER and you've got a smooth ER. What makes the rough ER rough? Ribosome. Okay, what is the purpose of the ribosome? They make proteins. Okay, so you'll hear us use the word synthesize a lot in class. Synthesize means to make, to build. Okay, so ribosomes synthesize proteins, or they make proteins. Okay, so the rough ER is considered the membrane factory. So all those proteins that the ribosomes are making that need to end up in the plasma membrane are done here at the rough ER. Okay? So the integral membranes that end up inside the membrane are put together here. Okay? We also make the phospholipids of the cell membrane. Guys, I still have 1 minute. You ready? Smooth ER. Okay, what did you put as your definition for smooth ER? What did you do? So he does what with that? So he's the synthesis area for lipids. He makes lipids. Okay, so smooth, no ribosomes. I remember this one because smooth and greasy kind of go together, you know, slick and smooth. And so smooth ER makes the lipids, okay, greasy. Okay, so lipid and steroid synthesis, lipid metabolism, and detoxification. Okay, so you guys have a quiz on Wednesday. Make sure you study the objectives for chapter 3. And your test will be on Friday. Let me know if you guys have any questions, and somebody feel cricket before you leave, please.